Wow. I don't even have to say anything and it gets around like word of mouth. Crazy out there. Yes, we probably will not have lab because not for this class, different class. It's quite hard, in my opinion, to do all the labs for Astra 2300 once you get to stars and galaxies and stuff. You just run out of like cool things to do in lab, you know, like there is a third one that I wanted to do, but I haven't finished like perfecting it. And so you saw how the asteroids one went. You know, you don't want to have a repeat of that. Okay, it's 1 o'clock. So let's start lecture. How's everyone doing? You're all on time. Let's go. Anyone who's not on time, like Reed. Just kidding. He's right there. I can see him. Here's the SOTIs. As I mentioned, I would love feedback on this class. The faculty would like to know whether or not fluids is something that you folks are interested in having as an elective long-term. Okay, we're almost done. So that must feel like either a great burden is coming off or that it's the most stressful time of one's young life. So I don't know what you're personally feeling. Both at the same time? Yeah. Yeah. So I really want to propose a 12-week semester. Late. You feeling better?
Much better.
Okay, good. That's all we really care about. We don't care about time as long as your health. So I want to propose a 12-week. I think that'd be good. I don't think anyone's going to listen to me. Like, what if you did 3 quarters that were all 12 weeks long? So quarters are too short, but semesters are too long. You don't like it? Right, currently, we're inside of week 13. Oh, sorry, whoa, shit. Wait, is this right? We're inside of week 14?
I think it's 13 because you added spring break as 1 week.
Technically, that's a week, though, right?
Yeah.
So yours is like, I think, a week.
Okay.
Yeah, because like the final week is like a proper place.
Wait, when is finals?
Finals is this week. Here. And we'll talk about that process soon.
No way.
Yeah, it's really soon.
Yep.
Yeah, so today we're going to finish up our discussion of boundary layers. We might get into Ekman layers, which is a form of boundary layer in a geophysical fluid flow. We'll talk about some other types of waves Wednesday and probably at the beginning of Monday. That's already May. It's May Day. Right, that's when the alarms are going off. I haven't studied at all. And then we'll talk about instabilities. And the instabilities are the cool stuff. That's when you see like the swirling vortices and you're like, oh, sick, right? And then you're done. So we certainly cannot get through as much material as I hoped, but that is okay. You know, that's just me being overly ambitious. And I'm hoping that you're still walking away with a deep understanding of, one, the equations that we've learned, and also some applications that might be useful. You have a question?
Yeah, but I guess I was wondering if final is going to look like if it's not a regular.
It'll be a longer appointment? Yeah. We'll probably talk content. Yeah, we're going to box one-on-one.
There's
Yeah.
generally no content for week 16, so from May 8th to like.
No, there is content. I just haven't filled it out yet.
That's okay.
Yeah, this will be like specific chapters in instability. And you'll notice that I didn't assign a homework this week because
Yeah.
you got to give me the homeworks that you've done.
Yes.
And at some point, you know, maybe geostrophic boundary layers are not stuff that you're interested in, or sorry, geophysical boundary layers are stuff that you're interested in. So we won't assign a homework on that. But pretty soon I'll just assign a homework that says boil water in computer. And you will boil water in computer. Because it's surprisingly hard. Great. Wonderful. Questions, comments, concerns? Yeah. Well, I would hope that the whole semester is studying for the final.
Yes.
Yeah. So if you thought, oh, I'll just, not do anything the whole semester and then I'll get an A because I'm nice to Mateo, that won't happen. Some people will not pass this class, I suspect. Yeah. They're not necessarily here, but that's okay. What? Right now, I would say that of most of the people who are here. They're look, if you turn in the homework, right? You get feedback on what you've written. Then I can be much more confident in your understanding. And I can say, oh, this person will pass the class. If you don't turn in the homework, then I assume you don't know it. And therefore you have an F in the class. Right? So that's the modification.
Okay.
Is that F for fair?
Yeah.
Okay. Questions, comments? Yeah.
It's like but like in terms of a higher grade than that, like what else kind of helps us add on to that beyond the homework itself?
What do you mean by that?
I guess like aspects
Do well in the homework?
yeah, oh yeah.
Yeah.
Oh,
There's nothing else in the class, right? There's understanding the material, there's participating, there's learning, but the way that I assess your understanding is through the homework, right? So the bare minimum obviously is doing it horribly. That's totally fine. You come back and you say, hey, I need help on XYZ, and I help you on XYZ, and you're like, wow, I really get it now. And you give me a version back that looks much better. And I say, wow, they really understood the material. That's an A, right? Versus not getting anything, having no information. I have a conversation with you and you say, well, I really like fluids. And I say, well, what do you understand about them? And you say, I don't know. Then it's really hard for me to know that you learned anything in the 15 weeks, right?
Yeah.
So the oral, we'll have a conversation. There won't be like math as far as you having to write out derivations on the board or anything like that. It won't be a written set of questions. It'll be a conversation, but it certainly will be a conversation that includes a conversation about content. So not like gotcha questions like, tongue twisters about fluids, but like, do you physically understand what is happening when a fluid moves? Make sense? Okay. Much more important in this class, for me personally, the idea that the concepts are understood. The mathematics is a vehicle to understanding what is physically happening, right? Anyone freaked out? Yeah, and then of course, failing to make a final appointment would obviously also fail the class. If that wasn't clear. Some people waited a really long time and they're not here either. Okay, ready? Question before we start? All right. What? Didn't mean to get you down so early in the morning. Okay, so let's talk about fluid dynamics. This isn't a picture of fluid dynamics, but it is pretty cool. This is two things that happened this week. I think this is in Iowa, which is pretty low, but this is aurora and meteor happening at the same time. So you had a storm from the sun that's shooting particles into the top of our atmosphere. Pretty. I mean, like, wow, cool. It's a palate cleanser, as we say. Yeah.
So it's like, they're just like cameras always taking things like everywhere, or does someone like see that?
These are like human beings. Yeah. So this is someone like on Twitter, and then they post it, and then I steal it, and I use it for my classroom. That makes sense? Okay. Oh no, this one still? Can we do this one? We understand all the terms, right? The first one? What's that? Yeah. And what does it describe?
The conservation of the
Good. And how would you, like, let's say you're talking to Desiree, like, how would you describe it to her?
like just the overall thing.
Yeah. Just not like term by term, but like, what would you say? You're having a conversation now. You're ready for the final interrogation.
I would say, conservation momentum is basically like. You can't have a moving car stop by itself. It has to like have. The energy has to go like somewhere.
Uh-huh,
So it has to be like transferred in a different, like in some way,
uh-huh.
whether that be like through pressure, through gravity. I don't know how to describe the other ones.
That's pretty good. It's pretty good, right? That's very conversationalist, right? That's the type of understanding that we want to have. Okay. How would you help him, Rolando?
And then I would say, oh, don't forget that fluids are viscous. One like natural like property of fluids, and there are, when fluids like move, sometimes they undergo like stress and strain, and like those last two equations follow like the stress and strains of the fluid.
Okay, yeah, and we don't even have to reference the equations, right? Now we intellectually understand these are the causes for generating momentum. And you say, like, now you've tag teamed really well, right? And you say, well, Jose jumps in, he's like, actually, that's great, but you're forgetting about a set of terms that are really important when you think about, say, the Earth as a whole. What would that be, Jose?
I mean, they pretty much said what I would have said. I mean, you're kind of describing the Earth as a whole. You could be talking about different pressure levels where you are located, or in the sewer terms like the Coriolis force.
Okay. Yeah, that bottom stuff, right? And so how would you like generally talk about that to Giselle, who wants to know more about the global scale models?
Well, looking at the bottom one, I would say the depth describes is it the vorticity and change in space and time?
Which one? This one?
Yeah.
Well, this is just the fluid momentum, right? So this is the same.
Okay.
And these are the extra terms that we're adding in.
Yeah.
But generally speaking, when we think about adding in planetary rotation or non-inertial reference frame, what are we adding? Anyone want to help here? Yeah.
Or maybe any fictitious forces.
Okay, so we're adding some fictitious forces from the fact that the place that we're looking at our fluid is changing, right? And so how would you describe that? Right?
Central fuel force.
Right. So that's this like extra piece out here. Anything else?
That Coriolis.
Coriolis force, right? And generally speaking, do we have these two others?
No, because most of the stuff that we look at is basically in just one hemisphere.
Not just one hemisphere. This one here does what?
Oh, that's a linear acceleration. So it's like a vessel our system is accelerating, and it's like we're just looking like very like just like one small thing in front of us, and we don't really need to about that.
If you think about the Earth rotating, is the Earth rotating, speeding up and slow down?
No.
No. So that's this piece gone.
Okay. Which piece?
Right, this piece. This is the change in the rotation rate. That's gone. And also, is the Earth like moving?
No.
It is, but we don't really see it, right?
Okay.
So geophysically, we can throw these terms out. And it's just like Eduardo said, you just have something that's Coriolis feeling and centrifugal feeling. And you talked about, we feel like there's these gravity terms. So maybe you're having a conversation, you say, well, really, we can think about the centrifugal term as like taking a little bit of gravity. Because if I'm at the equator, the fact that I'm spinning at the equator means that I'm just slightly lighter than I would be at the poles. Because I'm far from the center and I'm rotating, right? Success? Yeah. Question?
No, I actually just noticed this equation for the rotating thing is kind of the same as attracting the other forces. So I feel like a different one, if you added a new force to that one,
Sorry, so for this one here,
yeah,
these pieces.
it seems like it's the same as that one, it's just we added that. But like,
Yes, yeah, so this is the same equation. I just added these terms in.
or not, it's like not explaining.
And then I just dropped this one here. And the idea being that you can mix and match, right? So one of the things that I hope to show, or that we're going to see when we have these various discussions about what's appropriate in the fluid, is to say something along the lines of, okay, here's the full momentum equation. Here's all of the things that I have to consider. Now, what can I throw away? Right? So you write out all of the terms. And you say, well, this is a nuisance. And then you say, well, this term is basically zero because this isn't changing at all. Throw it away. Right? Or this term is basically zero, throw it away. Or you say, you know, I have all these things in here, but really I'm just looking at the flow in a pipe, and the pipe doesn't really care about the rotating earth. So throw away anything with the rotation of the earth in it. Right? And then you get back to this. Right? Or you're up here and you say something along the lines of, there's not really, maybe I'm looking at a thin layer of fluid. There's not a lot of changes in G. Throw this away. Right? So you write all of the pieces out, and then you get into this art form of throwing the things you don't want away. Make sense? Great success? Okay. So we were talking about boundary layers, though. Do you remember this? Okay, so what's happening? What are the assumptions that we made when we were talking about a boundary? Yeah.
The no slip condition at the boundary.
Good, right. So we said there's no slip at the boundary. Good. Anything else? Yeah.
Air doesn't like see the wing.
Yeah, the air doesn't see the wing far out. Good. Another way of saying that would be. What's that? Another way of saying that would be air doesn't see the wing far out. So the opposite of that would be the flow far away has fixed speed. Okay. And what are the momentum equations look like? Let's go back 1 second here. I can show you what we're writing. Right. We're going to say something along the lines of so this is this, right? Which parts have been thrown away? I told you it's the art of throwing things away, right?
Threw away body forces.
Threw away the body forces, right? How did I get to do that? We'll go back 1 second and we'll look at the picture. This is the physical interpretation here.
You're assuming that there's no really pressure change in the height.
In the height, yeah, there's very little changes in pressure due only to gravitational potential energy, right? That's an assumption about the way that we set this up. Okay, anything else? What else would I throw away? So this is gone.
Oh, what are we trying to do? Like what was
So I have this here. I wrote the momentum equation that we're going to be using to investigate the boundary layer conditions that we're talking about today. And we did this at the beginning or the end of last lecture, so we're going to do a little bit of a rehashing of this, but we're practicing here the art of starting with the momentum equation and throwing out the stuff we don't need based on the assumptions that we make in the physical situation, right? Is this present? No. Why not? Yeah, you can have a rotation-free object, but we also said something along the lines of we're looking, say, at a boundary layer like this. What did we say about the curvature of the boundary layer?
I think if you go small enough, then it will basically just be across with this.
Right, we said that the radius of curvature had to be really, really large. And that we would have basically only the assumptions of flow going up like this, or changing the, sorry, in the Y direction, for example. And the flow is moving over in the U direction. So you can. Come on now. Why did this just break again? Come on now. There we go. So here's what we're saying. We're not gonna have any flow through the surface. That was, we talked about the no slip boundary condition. And that it's only gonna vary along the edges here, right? And then as you just mentioned, that makes it irritation, right? Because what's the vorticity look like if you only have flow in one direction? All right, how do I prove that? What's vorticity?
You can see it's another plot. Oh,
What's that?
it's a
Something
curl
cross-
It's a curl.
Curl of something, good. Curl of,
Fluid velocity.
yeah, there you go. Okay, so let's prove that for ourselves really quickly. What's U? It's not X and Y, but it has components in X and Y.
So you X or U or
U, right? U of U and V of V.
Yeah.
Right, something like that. And in this particular circumstance, U is the one that's going in the X direction, has only components in X. Is there a V?
no.
No. Okay, so perfect. Done. Right?
Oh, okay.
All right, so let's get rid of that. Let's have only the compression. Right, so this is, why does this keep doing this? Sometimes I hate this computer. And that's every day, every single day I hate this computer. Okay. So we have this term. And this term is present here. You see that? This U is the one being operated on here. Right? Do I have a partial derivative with respect to time? No, what does that mean? There it is. Yeah, so I've assumed that this boundary layer is a steady boundary layer. So now I can throw away the derivatives with respect to time. Right? Okay, and then I'm done. I got what I need. This is gonna drive me insane. Someone in the chat that is talking, that's one. Okay, let's find out. There we go. There we go. Okay. So let's work this out. I asked you to find some important scale sizes. Where did I just put them? We wanted to look at the contributions from each of these terms. And I said, how big is this term? Remember?
Is that the way? Is that something?
Wait, we're gonna get there in 2 seconds.
Okay. Wait, repeat that.
Yeah, there's an L in there for sure, right?
Hmm.
What else?
Sorry?
U squared, very good, right? So this is like the way that we looked at the dimensionality. We said U squared infinity over L, that's like the size of the effective term. Right? And then what about this term over here? How big is this term? Okay, so I got a U infinity, good. And it is a length, sure, but how many lengths? Two lengths, good. Anything else? Yeah, it's a new, but yeah. Good.
Oh, no.
Okay, and then we said something along the lines of that this length here, the effective length, was the one over which the wean is occurring on. Whereas the appropriate length scale for which changes are occurring for viscosity is in the direction, the normal direction to the surface. And we called it something different. We got a result that said that this will instead not be L, but maybe delta. Right? And we said that we could write delta in a fun way. Okay. Write delta over L. Approximately 1 of the square root of Reynolds number. Right? Remember that or not?
Yeah.
Okay. So what do I mean by when I say that? I'm basically trying to say that the advective part and the viscous part are going to be comparable in the boundary layer. And how do I intellectually know that this is true? It's because of a few assumptions. One of which has to do with inspection, right? Thinking about this as a problem. Here I have advection. Fluid flow is moving from left to right. Okay. Yet at the surface, what happens? At the surface here? It's not moving. So viscosity has to get rid of that. And we said that the way that we generate or lose momentum is through these terms on the right-hand side. Right? So this is the term that's eating up the advective term. Right?
That's where that momentum is going?
That's where the momentum is going.
Oh.
Now, of course, we're going to talk about the pressure here in 2 seconds. We talked about this idea of doing dimensionless scaling so that we can apply this in general. So we can do that again here. You can say something along the lines of, maybe I'll write it down here. Okay. So what is this basically saying? So let's write some more terms out here that are important. That P infinity is the pressure that's felt way out here in the undisturbed flow, just like U infinity is the flow that's felt way out here, right? And all we're gonna do is we're gonna go into our momentum equation and into our continuity equation, and we're just going to make these substitutions. The idea being that you will get a version of this equation, but in these dimensionless coordinates. And then what you'll see when you have that as it's written out is things are written with the Reynolds number baked right into it. Right. So remember how we wrote the Reynolds number? We defined it. Right. This is the ratio of the effective term over the viscous term. But now we'll see that as a real number, you'll make terms bigger or smaller. So I can rewrite this whole equation up here, okay, in a dimensionless form like this. All this. If you're curious about how that substitution moves around, that's just in the continuity equation. Right, those two things equal 0. Okay.
What does that mean?
This is in dimensionless coordinate systems, so it can be applied very generally, right? Under all of the assumptions that we've made so far. So if I do 1 over RE squared, and RE squared over RE is the Reynolds number, what's a good example of when Reynolds numbers are important for a flow to be considered, say, turbulent? As opposed to viscosity is not important versus important. Yeah, like under 2000, right? Okay. So essentially what this is saying is we have a large number, right? When the Reynolds number is large, what happens to this front term? Yeah, it's approaching 0. So that makes this term here very small. And you have a balance then between this term and this term. Right now you say, well, this is still 1 over RE. That's not as important as 1 over RE squared, right? Whenever you look at terms of this type, they're terms of order, right? Another way you can do this is you can multiply through on each side. 1 over RE becomes, you add an RE here and 1 RE here, right? That would be the same way. So it's just the way of scaling the different terms in the momentum equation, right? Okay. Let's have a look at this one here. Oh God, this never wants to work. Okay, so this is an example of when you go through the process of doing the math, which I'm happy to have you guys. Would you prefer to like go through the process of setting the boundary conditions and finding the solutions here? Yeah. Option B is to just describe it intellectually. Okay. Okay. All right, so we're gonna do a couple things then. So I'm afraid this piece is out. The relevant equations for laminar boundary flow in dimensional form are written as such. This is only for R, E heading to infinity. That's what. That's continuity. And then this thing we've already just seen. Just writing it again. We're going to talk about the terms. So the important piece here is this first, we're going to start backwards. And we're gonna, this piece here tells us that the pressure is constant in the boundary layer. Right? That there is no pressure gradient with respect to 1. right? Or that it's the PdZ is a constant. P is a function of volume. Okay. If the exterior flow here, this part is known and it's laminar. Remember we talked about this being a laminar flow very far away. And then as we interact with this object here, you create a small region, very small region, that's the boundary layer, in which the velocity goes to 0, because viscosity does become important. But outside of it, it's irrotation, right? Out here, it's fully irrotational. And here, it's going to change, right? Okay. But these two assumptions of exterior flow being known and rotational, fluid density probably being fairly constant, assuming that your wing is going through a nice fluid, then you can just use Bernoulli's equation, right? That's the special form of Bernoulli's equation, where that just says something along the lines of, assuming, of course, G is not important, P plus 1/2 rho mu naught squared is a constant, right? Throwing away the body force term. Okay. So then we can differentiate this. Minus 1 over rho. It's just going to be equal to u. U, where U is the condition at the edge of the boundary layer. Okay. So we had some other conditions as well. We said that U at the interface here, the no slip condition, and also the no flow through the wall is nothing is going through the boundary. This is across on the boundary. And similarly, we can say that U, all locations, but for Y very far away, is that other U infinity. There's a smooth transition between this and this might go into 0. It's that little piece that we see at the bottom. Okay. 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 That's it. Yeah, there's an inlet boundary condition which talks about the fluid flow that's coming in from the left compared to how it's changing as it's going out on the right, as a function of height. But the important thing to keep in mind here is something about the boundary thickness. Okay. So an important question here is how big is this boundary layer? And just intellectually speaking, what we want to be thinking about is how far do I have to go away from the boundary in order to get back to a condition where my velocities are matched to what they started with, right? That is what we typically think of as the boundary condition. And in practice, we see that the boundary condition for something like a 2-meter size wing is how big?
Just like a centimeter.
Just like a centimeter, right? Those are the numbers that we keep in our head. Boundary layers are thin and they're small for laminar flow. Okay, and as we'll see, it gets more complicated as we begin to turn that crank. This is one version of the formalism that can be done exactly. But as I mentioned earlier, almost all fluids can't be done exactly, right? They need computers. So here's a version. Why? I'm going to destroy this computer. Okay, this is a wonderful figure in the textbook, which shows that I'm not the worst artist. Because scribbles on the side. This is a textbook. This is not me drawing on top of it. Okay. So over here, you have the full Navier-Stokes equations for Reynolds number of 1. Okay, and Reynolds number is going to increase as I go to the right.
Okay.
And what does Reynolds number increasing mean?
More effective versus this.
Generally speaking, when we think about Reynolds number larger, we think of viscosity being more important, and it's sapping off energy, right? It's leading to turbulence. And you see that here. Okay. So even though they're larger than 1, you're going to get laminar boundary layer equations. That's what we just saw. These are laminar boundary layers. They're flat pieces, and then above them, the flow itself continues. So if, for example, we went backwards and we looked at this picture, oh my God, I'm going to kill this thing. Okay, here the flow goes to U infinity, goes over the wing, and then what does it do afterwards?
Go back to.
Goes back to normal, right? That's an assumption of the flow, right? So that would be a version of laminar flow, one where it acts like layers that are separating around this wing and then converging back together. And the reason that it does that is because we made an approximation very close to the wing where we said totally different rules are going to apply here. Okay, I'm going to treat this separately, and then I'm going to connect the solutions. This is a great way to do physics. Okay, out here, undisturbed. Here, special. And then just smoothly connect these two physical regimes. This happens all the time in real physics. Doesn't happen in like throwing a ball, but you get it. Okay. Oh my God. I'm going to delete this. How do I delete? Okay, here we go. Okay. So here's that example. No slip boundary condition. We get far enough away. You still have a thickness here. Okay. Then you start getting up here to this idea of a region where you have self-similarity, but now you've sort of forgotten the initial condition. And at some point, the Reynolds number gets large enough that you get non-laminar flow for the first time. And this is that transition region between when we think of flow as living in these layers to now them breaking up. And that breaking up tends to have little eddies and vortices associated with it. And as we're going to see in a few seconds, this becomes a highly unstable type flow. Okay. And then, okay, so here you have wiggles. And they're like chaotic wiggles, but notice that they're still bounded. Okay. So there's an important definition when we think about the idea of chaos. If I drop something like this, right? Okay. Maybe that's not a good example. If you drop a ball, you can like predict where it goes, right? So you give like a initial condition, and then if I slightly change the initial conditions, you could say how different will the end trajectory be. So if I throw you the ball and I throw it like this versus if I throw it slightly lower, it's going to end up very close, right? Far away. The condition for chaos, the condition for instability will be similar initial conditions, give widely different final conditions. Okay, so if I threw it like this, and then I threw the same ball just slightly differently, but it ended up over there, you'd say that was a chaotic condition, right? This is what you get when you have a roulette ball. So the reason why you can't win at roulette, despite people trying to do this exactly using computers in the 80s and 70s, you drop the ball. And every time you drop the ball, you think, well, that's just normal physics, right? That's like dynamics. I should be able to figure this out. Well, every time there's very slight changes, and they start to add up, and they create chaos, okay? The analogy being here, these initial conditions, they stay kind of close. It's not quite chaotic yet. Whereas here, the initial conditions wind up, and these are really good drawings, right? They wind up very different depending on where those initial conditions are. You end up with totally different results in the fluid. And we'll see that when we see the fluid as a whole. Okay? And then you have full-on turbulence. And turbulence is you just have to treat it differently. It's not laminar anymore. Okay? Questions? Okay, here's the example of where you see it. Is there anything else I should tell you about this? Yeah, let's show you this part here. This is fun. Oh my God, I'm gonna kill this thing. Here's an example. So here you have a flow in a flow past a cylinder, which is one of the traditional like fluid dynamics. Okay, so this type of flow is what? Laminar. Okay, you have lines, they go around, they come back. You can also tell that because RE is 4. Right? Very clear. Okay. There is certainly a boundary layer here, but inside that boundary layer, it will be laminar. Okay. What about this one? Okay. What's that?
The middle one between laminar and true.
Well, don't look at the middle one yet.
No,
I just want this one.
the 3 stages. You know, like laminar or something, and then one to T.
Turbulent.
Yeah, it's the middle one. With like somewhat.
That one's turbulent.
No,
All right, just ask about this. Don't look at the whole thing yet. Imagine that I actually was smart and I put like light on these or something. Okay, just up here.
Transitional.
You think this is transitional already?
I'd say laminar.
Still laminar? Okay, we have a vote for transitional. Vote for turbulent. Vote for laminar. Vote for I don't want to vote. Okay, oh, all right. No one wants to not vote. Okay, so what do we think here? What makes people feel like it's laminar?
I feel like it's laminar because, with like little, can I call those eddies?
Sure, yeah, you can call
Yeah.
this. What would an eddy be? Like a little circle, right?
Mhm.
Circular motion. So maybe there are eddies developing behind you,
Yeah, and then it's like constant.
but back here, the streamlines are constant.
Yeah,
Right?
it's only like a little section of it, I guess.
Right, yeah.
So like the starting conditions is the same as the final condition.
The starting conditions are the same as the final condition,
Ooh.
right? So the lack of, when I look far away, the lack of asymmetry tells us that it's still laminar, which is really important for the laminar condition. Okay? Okay. What about this one?
Yeah,
Is this laminar?
definitely not.
Okay, so this one's finally changing. And this is our favorite one. These are the von Karman vortices. Okay, it's kind of laminar looking,
Yeah, it is.
kind of. There are like lines. So this one's pretty cool because you get these instabilities developing. So you'll notice that the streamlines they go on here and then they like turn back on themselves. It's very weird.
Mhm.
And they're gonna deposit kinetic energy at the bottom of these little vortices. But these vortices are gonna be out of phase and they're gonna move as they go down the flow. And so that's obviously a snapshot. So this is in your transitional regime. But far enough away, let's say you start up here, okay, goes around. It's actually, the outside pieces out here are going to look laminar, even though the interior will not. Right? So that is that transitional region we were talking about, that the initial conditions really matter. You end up with sort of different, let's go back here, right? You have some instability here and it's bounded, not running away to wherever. Gonna be either on one side of these vortices or not, right? They're close, but they're not perfect. As opposed to here, right? Start up here, right? Small inundations. And then here in this larger Reynolds number, you get turbulent wake. And that's just the scribbling that we saw before, right? So this one here, you have a Reynolds number of 3 × 10⁵, and you still have a laminar boundary layer, okay? But the wake behind it, the flow behind it, obviously has asymmetry, right? And the asymmetry is coming from the fact that you are depositing initial momentum into vortices, right? We talked about how in when we were writing the fluid equations, we included the fact that there's entropic processes, right? Ones that show the directionality of time. So for example, entropy increases in a system. We talked about that. More chaos. This one, you can play U backwards and forwards. There's no viscous property, which is creating a directionality. This one, not so much. Right? This one here certainly has a specifically one-sided time. And then by the time you get to here, you have a turbulent boundary layer, which is something we're definitely not going to get into in this class. Okay. A boundary layer itself has vortices in it. Okay. Stupid, yeah. Okay. So what does this really look like? Kind of cool, right? This is a von Karman vortex forming behind a cylinder. And as you can imagine, that is done on a computer. So it's possible, right? Okay. So all they did here, this is not telling you the magnitude of the velocity. This is just showing you where these particles ended up. Right, so they color them, and then you watch them fly behind. Okay. Does this ever happen in real life? Yeah. When it hits a building. Yeah, good idea. So I like those length scales. I'm going to go a little larger on us. Do you see it? What is what? Yeah, good question. Yeah, there's like a little mountain right here. Okay. And then what's the fluid flow? Which direction? Yeah, it's got to be in that direction, right? So we notice the von Karman instability is giving us directionality in the flow. And you can see some little spirals develop all the way backwards. What? Okay. So we can do that with a cylinder in fluid in a lab, or we can do that with the earth. Okay. Okay, here's some other examples. We talked about whether or not human beings in water are what the Reynolds number is. Do you remember that conversation? Turbulent. Humans are turbulent, right? What about small fish? Laminar. Okay. What about let's see, I'm reading them because I can see the preview. Okay. What about bacteria? Laminar, right? Have to be laminar. It's too small for those flows, right? The length scale. We write the Reynolds number definition out again. You see that it's UL over nu, right? What about blood flow in the aorta? You know, blood flow inside of your heart. Is that laminar or is it turbulent? Laminar? Yeah, what would be better? Does anyone know? Why would laminar be better?
I was gonna say like the initial condition of like the heart pumping blood out, you know, if you not out with laminar, and then it's like the heart always does like a constant beating, and that's like a, I don't know, I guess that's like an initial condition, I guess.
Okay, let's think about this example up here, right? These clouds here are still moving to the right, right?
Yeah.
So like if you have, you know, turbulent blood flow, you don't, by the way. Well, the difference here is not quite what people are talking about. When we have, you know, turbulent blood flow, the blood is still going to get from point A to point B, but something very important is happening. That's different when you have turbulence. What?
Depends on time.
It does depend on time, but so does, you know, right? Because you hopefully your heart is pumping it through your lungs, and then your lungs bring it to your body and it's oxygenated, etc. So there is already a time flow in your body. That's not what I'm worried about.
I was gonna say it's kind of like This is a beat almost, it just throws the whole system off.
Remember, we want to think about what the actual value of the turbulent flow is doing.
Creating more viscous forces.
More viscous forces, and that's doing what?
Slowing it down.
Slowing it down. Remember that these are momentum equations. And if the viscosity is really important here, right? I mean, obviously there's going to be viscosity on the walls, but you're going to be sapping off. It's going to be harder for the heart to pump, right? Okay, those just those terms up there. We can see that. Okay. What about blue whale?
You mean in water or sorry?
No, sorry. Yeah. Good question. Good question. No, just blue whale in water. Swimming.
I think it's turbulent. The humans are turbulent.
I think it'd be turbulent, but less than us.
Okay. All right.
Oh,
Interesting.
we really can't meet. This is what.
Okay, raise your hand for laminar. 2 laminars. Raise your hand for turbulent. You're pro laminar? Okay, three versus.
Oh, no, this is turbulent.
You want turbulent.
I want to.
Who wants turbulent? 4. Who doesn't want to vote? Okay. All right. What about large ship, big ships? Titanic. Turbulent. Everyone likes Okay. What's that? Big ship like the Titanic. It's got a
Above or below
in the water with propeller, steam. I don't know, something like that.
I want to say laminar for the ship.
You said laminar for the ship.
That's turbulent, like 70% of the power's energy is on turbulence. It's like nice.
Okay. Okay.
Like also for me, like why I said laminar, so you see the water like flow around the ship, and then it kind of like patterns back. You know, like you see like the waves like colliding afterwards, or like them spreading out. Like because it's like the same initial conditions of the water.
Okay. So Rolando's hypothesis. Okay.
All around.
Here's the boat. Okay. And there's bow braking. So it does this very smoothly. Okay. And then what does it do, Rolando? Does this?
No.
Does this happen for some boats though?
I remember. I think so.
Yes.
I remember it.
Yes, it can happen for some boats, but what's really important here? The shape of the boat, that's certainly important because of
Oh.
why are dolphins like dolphins?
What?
Why are dolphins like dolphins?
Longer than they are wide.
And also they do this like,
Longer.
I didn't do it good. This is the dolphin. This is the Crismani dolphin.
Which
This is the dolphin.
Well,
Okay, this is the nose, and the flow is going this way. And it goes over and back down.
oh,
Is the dolphin turbulent?
no, it's laminar.
Yeah, transition.
Dolphin tries its best to be laminar, but what's his major problem?
Global.
In terms of the physics that we know.
Maybe it's the nose. I don't know. Oh, it's long.
No, hold on. I'm writing L. What other things we know?
What are they? Oh.
What's that? Dolphin fast. If U is large, you also have a problem. So in our big boat example, U is large and L is large. So in fact, you would not expect the flow around a big boat to be laminar. You'd expect it to be quite turbulent.
So are manatees less turbulent than dolphins?
These are all very good, very testable questions. So a seal is not laminar, I would suspect, because it goes very quick. seal fast, but in the water. Seal slow on the land.
Also, whales are laminar.
Whales are not laminar. They're way too big. Okay. Manatees, I think, would probably be right in that transitional region, but they also just go slowly because they're lazy, right? They have no business appointments to get to, right? They're not chasing down fish. Dolphins have to be fast because they're chasing down fish, right? They're eating things that don't want to be eaten. They have to go very fast. And so all objects that are in the water or that are like aerodynamic, fluid dynamics, so to speak, are trying to reduce turbulence. Why is that? Say that again. Sorry, one person said it, and then I didn't.
It takes up too much energy.
Takes up too much energy. Why does it take up too much energy? So we had it up there, right? Turbulence saps energy. So you'll look at 18-wheelers, right? Have you ever seen an 18-wheeler?
Yeah.
Never. Okay, I'm gonna advise you go outside more. Okay. And you see this, right? Do they make 18-wheelers like this anymore?
Yeah, they do.
No, what do? Yeah, they make them curved, right? So they can do like something like that. Okay, okay. And then what else? They do a really funny thing at the back.
Give them like long panels.
Yeah, they give them long panels. What is that supposed to do? What's that? Help the airflow so it won't. That's exactly correct. It's exactly correct. So you have some streamlines. And normally, let's remove this. Okay, normally this would just go really well drawn, right? And so the point of these panels is to create a taper so that the airflow goes like that. And you still get some here, but the turbulent wake behind the truck is much less. And therefore the drag on the truck is much less. Let's keep in mind what we're talking about here. We form a boundary layer on the truck. This is air that is sticking to the truck and it's not moving. So as the truck is moving, it pulls all of the air around it, right? So you notice truck goes by you while you're hitchhiking, you get blown by all the air, right? That's literally it moving through, and it causes additional energy to move all that air. So if you can change the boundary layer, you can drag less air behind you, right? So it might actually be useful to know.
Why is it more fuel efficient to drive behind a big rig without?
Very good question. So why, it's called drafting, right?
Yeah.
Why do people want to draft?
Or like,
What?
doesn't it like move with the car?
So you can hang out right here, right? This is where you die if they crash, right? Or if they stop. But it's theoretically it's a little bit more efficient.
Not efficient enough.
A little bit, yeah.
I've done a lot.
Is it worth dying for? We say a lot, you know, you gotta quantify that.
Like, I went from like 240 kilowatts an hour driving to like down to like 130, 140. It was a lot. It was like half.
It's pretty, okay, fine, everyone get 5 feet behind. No.
Yeah.
just kidding.
Right?
I was really a long battery. I had like
You had to draft in order to survive. Okay, so what's happening? Right. So what's happening is you're entering the airstream here, right? Remember that far away, okay, it has whatever conditions it wanted with, right? And it gets broken here at the front by something that we haven't talked about yet, which is called a shock, right? We are not in any way saying that cars are laminar creatures. In fact, they're usually not. So airflow usually is piling up in the front of this in something that's called a shock that we may or may not get to. Shock, all right? So you can have partial shocked conditions. But basically what you're gonna have is you're gonna have a pileup of air that sits in front of the object. And that air pushes the air in front of it. Now, the nice thing is that's gonna deflect that air on either side. We've kind of seen that already, right? A little pileup region, that's the boundary layer. Does that make sense? Okay, so you have a transition on this side. It's actually not hard to understand shocks once you have boundary layers. You have U infinity out here, and then down here you have 0, and you have a smooth transition. That's essentially the shock region. But setting up that shock region takes energy, and maintaining it takes energy. Now you just sit behind here, right? And there's less of a shock on your car.
Oh, less of a shock.
Less of a shock. Still a shock. You're not like inside of the streamlines.
So bullet isn't laminate?
Good question. Bullet. No, I think the velocities would be too high, especially like a fast bullet. So a fast bullet, think about it in the context of fluid flows. So in air, sound of speech or sound speed of sound, I should say, it's like 300 meters per second. Bullets travel much faster than that. So you usually feel the shot before you hear the shot, right? So therefore you're in a shock condition. It's definitely not laminar to be shocked. And I'm saying shocked, not shocked. Questions? Okay. Yeah. Yeah, that we're not considering that here. We're just imagining they're already at speed. This is generally true even at speed. So 80, 90 miles an hour would still be true. It's not. So thinking about driving a car, the velocity difference between so I think it's above like 65 to 70. You're getting dramatic decreases in your fuel tolerance or fuel efficiency. Yeah. Faster you go in every car, down your mileage goes.
So like planes that fly above Mach 1, are they technically laminate?
Okay, interesting question, because now we're getting into two different discussions, one about shocks and one about planes and describing Mach speed. So Mach speed was one of the first, we talked about dimensionless numbers. What did Mach speed mean, since you brought it up? What?
Speed of sound.
Where? On the bottom, good. The velocity on top, good. Okay, so this is the most straightforward one that we can think about, right? Because this thing here is the speed that you're thinking about, the plane, compared to the local sound speed. What does the local sound speed depend on? Right, another way of saying that, what's the physical properties it depends on? Density. Temperature, good. Okay, these are the properties of the fluid that describe how well it can propagate waves. So let's say you're traveling at Mach 1. Okay, you need to make sure first that that's not described for the ground, right? Because the sound speed might change very dramatically at high altitude. Okay. So once we've gotten past that just little difference in nomenclature, if you're traveling near the sound speed, even 70% of the sound speed, you will become shocked. And what that essentially means is, as we saw before here, okay, maybe I'll do this one. This one is a better example. Okay, on this side, we can think about streamlines, and we can think about flow coming from you far away, going around an object and coming back. You can also think about this as communicating the fact that there is something here by the presence of these lines. This does not happen in a shock. In a shock, it has no idea that this thing is coming, and it simply looks like normal streamlines and then a thing, and then like turbulence behind it. So no, very much not laminar. But if you like shocks, maybe we'll do that instead of instabilities. Can take some thoughts.
What instability?
Instability is like why does water boil?
Oh, okay.
Versus like why plane go bing.
It's more important than pressure we're gonna be putting water boiling.
But we can also do why plane go, right? Okay, so let's put these ones up here. Here's your, this is the one we didn't talk about. I guess there's two we didn't talk about here. Oh, this one's great. Major League Baseball. Knows. Paolo knows. Big baseball fan, Paolo.
Oh, yeah.
So a typical pitch in the major league.
Past time.
Turbulent, non-turbulent.
Has to be turbulent.
Turbulent. Why?
I decide.
Ball go fast. Ball go very fast. Paolo not hit ball. Paolo claim he hit ball. Paolo not hit ball. Okay. Atmospheric tropical cyclone. Turbulent, non-turbulent.
Turbulent.
Yeah, of course. What is this one a joke? This is a big one. This is a big number, right? Okay. What about what's that? Okay.
RP.
Am I missing any in here? Blood flow in the brain. Thankfully, not turbulent. That would suck, right?
Yeah, it's even less turbulent than blood flow anywhere else.
I mean, consider this for a moment, right? So you have brain, let's say this is a brain tube. I don't know what they're called. Veins?
Yeah.
Something like that? What?
Capillaries.
Capillaries. Okay, so let's imagine there's a blood is going in. Okay. And if it's laminar, it's like this, right? Nice. And so then I have something in here, red blood cell,
Mhm.
right? Red blood cell is taking oxygen, delivering it to the cells that need it, and then taking away the carbon dioxide, right? That's the point of blood.
Mhm.
Everyone knows this?
Yeah.
Okay. Do you know this?
Yeah, I didn't know they took carbon dioxide.
That's what I'm breathing out, right? Thank God. Okay, so now I'm delivering it, right? And I let you off and then I grab it back on, right? Something like that.
True.
Imagine for a moment if it was turbulent in here. So same example, but now this one goes like that for a little while.
Ooh.
And so instead of bringing this nice, rich, oxygenated blood to where it needs to go, it goes on a little bit of a tumble for a little while before continuing.
Ooh. It'd be very.
You could die. Right? It would not be good. Okay, cool. All right, we never get through enough, but we are going to do an example of this. We're going to talk about Ekman layers. They're cool. Ekman layers, yeah. You get to learn what a hodoscope is or a hodograph. Yeah, that's what they're called.
How is it spelled?
Hodograph. Hodograph.
That looks like
Oh yeah, it's right here.
oh, just read it off. That looks like the
Oh.
golden ratio.
It's not.
Oh,
That's okay though. What's happening here is we're looking at say a free surface interface and thinking about the boundary condition where I blow on the water with wind in one direction over a large scale. How does that velocity propagate downwards? And now that we understand viscous boundary layers and how they can be correlated with the flow, we'll also introduce the idea of a viscous boundary layer and the Coriolis effect. And we'll see there's a balance there that's possible. So we'll talk about Ekman layers very briefly. We'll talk about other types of waves. So if you want to prepare for Wednesday's class, I would recommend getting into chapter 13 a little bit more. And then also making sure you understand this chapter 10 stuff. Okay. And then as mentioned, you want extra credit on this class?
I did one of the sodiums.
You did, you're the one who did one of the SOTIs?
Yeah.
Only 2 of them done it. So I will just assume if I don't get 14, that you didn't do it and you're the one who didn't do it and then not give you the credit.
Okay.
Does that make sense?
So I get credit.
No. If I don't get 14, I will assume that Rolando's the reason. And I'll assume that for every one of you. What?
I figured a little check mark.
You could say that, but what if all of you email me a check mark and then
Let's do it, guys. Let's do it.
you no, I can't see them. They're not allowed to be shown. That breaks the confidentiality of the SOTI. Questions, comments, concerns?
No.
Yeah.
If I'm driving my car.
Yeah.
With a tailwind at the same speed as my
With what?
with a tailwind at the same speed as my car. We'll be going on.
Oh, so you have flow going like this and you're driving like this? A lot better conditions. A lot better conditions. So think about like, so we, for example, we like to fly in the jet stream across the United States. So there's at high altitude, there's prevailing winds. And they move from the west coast of the US to the east coast of the US. Okay. Or maybe I mix that up. There's a preferred direction. Okay. Flying into those headwinds is awful. Flying opposite to them is great. So one, you can travel faster because the wind is literally carrying you along and the momentum is helping you, right? So you're being invected. You are flow and you're moving through the flow with the added velocity. Make sense? Yeah, you want a tailwind if you're driving.
When you look at your energy the energy icon on your car, and it says like a northwest headwind, that is like 1% on your drive.
I go too fast to notice that.
Really?
No, I'm just kidding. I will look at that though. I will look at that.
Yeah, it'll tell you, it'll be like, oh, like it reduce your range by like 1%.
Oh, really?
Yeah.
Interesting. Little measure makers. Questions, comments, concerns?
No.
Okay. They're ubiquitous ducks.